So folks, we're continuing on in our discussion of nth roots, but before we do so, we have sort of a sticky issue that we need to discuss. And this issue is often skipped over or glossed over your first couple of times studying roots. And so you may not have seen this before, but it's time to learn it here. So the issue, it has to do with taking even roots of variables. Taking even roots of variables. So let's just set ourselves up. If we were to take the square root of 6 squared, and we could actually work this out the long way. We could say the square root of 6 squared would be the square root of 36, which then the square root of 36, remember that we talked about this in the last video, we're looking for the principal square root. So because this is an even number, or excuse me, because this is a positive number, we want it to return a positive number when we take an even powered root, and so this would be 6. Even though negative 6 is also a square root of 36, when we're looking for the principal root, which is what this symbol tells us to do, we're going to give the answer of 6. Now, here we're going to ask you to take the square root of the variable x squared. Okay? And normally this would actually be kind of a delicate procedure, but here I'm telling you, you get to assume that x is greater than or equal to 0. So if that's the case, when we go to find the square root of x squared, because we're being asked to find the principal square root and x is positive, then when we go to answer the question, we're just going to end up with x. So in that sense, because we know that x is greater than or equal to 0, it's as if the square root operation and the squaring operation, they're inverse operations of each other, but that's only true because x is positive, and we return just x. Okay. So far, I haven't done anything alarming. It's in the next two examples that things get a little bit more confusing. So let's go ahead now and evaluate the square root of minus 6 squared. So in this case, the square root of minus 6 squared is going to be the same thing as the square root of 36. And again, we're looking for the principal square root here, so we're going to give the answer of 6. It's the same answer as we had before. But the thing that I want you to notice is that students might be making kind of an assumption. Hey, when I have the square root of something squared, it'll just return that same expression as it did in these first two examples. But notice in this example, we're taking the square root of negative 6 squared, and it did not return negative 6. Because it looked for the principal root, it returned 6. Now, there's nothing too surprising about that. If you just did the computation, you would see that. Where this gets what I'm calling tricky or sticky has to do with taking the square root of this variable x squared, where here I'm telling you x is a negative number, like negative 6, for instance. So in this case, when we go to take the square root of x squared, we do not end up with x. We end up with negative x. The same way this happened here. Here we had negative 6 being squared, and we ended up with the opposite of negative 6, which is 6. So here I've got this negative number being squared. We're going to take its square root, and when I do so, I end up with the opposite of that variable. Okay? So this is what we usually do in this example, where we're taking a variable squared and we're finding the principal square root of that. Notice I'm not assuming anything about the variable. I'm not assuming that it's greater than or equal to 0. I'm not assuming that it's less than 0. So when we go to take the square root of x squared, we will just put the absolute value of x, meaning if x were positive, or 0, it would return x, just like it did in example B here. But if x were negative, and we were evaluating that negative number squared and then taking the square root, it would return the opposite of x, just like it did in example D here. So depending upon the sign of x, we get some different value. We either get x or minus x, and so that's why we go ahead and leave it with that absolute value of x. Now, if you're saying, I've never seen this before, I've always just written x, your prior math books or math teachers weren't lying to you. If you were to go back and look at the directions, they would always say, assume the variables are positive, and that's why you didn't have to do absolute values. But as you go further along in your math career, we're going to have to deal with expressions like this and work with expressions like this, and so it's important to see that this absolute value expression is starting to show up. Okay? Now, this is not at all an issue when we're dealing with odd roots. So this is only an issue with even roots, and whether and how we evaluate the even root for a variable depends on the sign of that variable. Okay? So when the roots are odd, it's not an issue at all. In this case, if you were to take the cube root, let me scoot over here a little bit. If you were to take the cube root of 6 cubed, well, that would just be the cube root of 6 cubed is 216, and the cube root of 216 is just 6. So likewise, if we took the cube root of x cubed, there's no problem here. Even though we're assuming x is greater than or equal to 0, there's never going to be a problem, and we just end up with x. Likewise here, if we take the cube root of negative 6 cubed, this would be the cube root of negative 216, which is again negative 6. So notice that in this case, we were taking negative 6, we were cubing it and cube rooting it, and those are true inverse operations of each other, and we return back to negative 6. That was not the issue that we had over here because of this implied 2. This was an even root that we were taking. And so we took negative 6 squared and square rooted it. We ended up with the number 6. Those were not true inverse operations of each other because the value of the original value was negative to begin with. That is not an issue with our odd roots. So in that case, when we go to take the cube root of x cubed, even though we're assuming that x is negative here, there's no problem. And so this would just be x. So always the cube root of x cubed is just the number x. But the square root of x squared is the absolute value x if you're not making any assumptions on the variable. So let me just summarize that for you. So down below here, we'll summarize that. So what we've just shown is that if you take the nth root of x to the n, and we know that n is an even positive integer, how do we do it? It would just be the absolute value of x. But if we take the nth root of x to the n, and n is an odd integer, then the answer is just x, no absolute value required. This is a very sticky issue. It takes a while to get comfortable with it, and usually it's just glossed over your first couple times of learning about nth roots. Why? Because they say the teachers feel that it's difficult enough to learn these nth roots. We don't need to throw in this extra hoop, and so they always just assume. If you go back and look at the directions, they assume that the variables were non-negative, and that allowed you to go ahead and not worry about absolute values in either of the two cases. So again, the big takeaway is that the nth root of x to the n is just x. Those are inverse operations if n is odd. If n is not odd, then it depends on the sign of the variable that we're taking that we're applying this to, and so we write the absolute value of x if n is even. Hopefully this explanation helped to clarify why that's the case. Okay, so let's continue. We have 3 properties that we want to talk about for our nth roots. I'm not going to derive these, and in fact, we're going to soon make a connection between nth roots and exponents, and you probably have already seen that before. We'll soon make that connection, and it's there that we'll justify these properties a little more carefully. So here we have that the nth root of the product of a and b is equal to the nth root of a times the nth root of b. What I want to emphasize here, I didn't write it, I'm going to have you put it in there. I want to emphasize that this is the product of multiplication here, this is a product, multiplication, a times b, and there we would have the product of the nth root of a times the nth root of b. So the way I want you to think about that is that nth roots distribute over multiplication. And I had you put those dots there to remind you that it's multiplication that they distribute over. We need to be really careful with this. Here we have a very similar property. To be honest, this property and this property are identical properties, but we usually present them as 2 separate ones. Here I'm taking the nth root of a quotient, and that's the same as the nth root of the numerator over the nth root of the denominator. So here we would say that nth roots distribute over division. Okay. And then we have this last property that says taking the nth root of a to the m is the same thing as taking the nth root of a and then raising that result to the mth power. So let me just, this one's a little bit of alphabet soup, so let's just clarify this. An example of this might be if we were to take the cube root of x squared, that's the same thing as the cube root of x squared. And so what we're saying here is that roots and exponents commute with one another. All right. There's one error that I feel like students commit so often. It's a very easy error to make, that I really want to give a name to that error and make sure we distinguish between what I just said in the properties above and what sometimes students misconstrue that to be. Okay? So let me zoom out just slightly here. And so we just said above, in part A here, we just said that roots distribute over multiplication. We saw that. Here was the operation of multiplication. We were taking the nth root of a product, and so the nth root of a product is just the product of the nth roots, assuming all the underlying roots exist. Okay? So that's what I've just shown you here, right? Here we're taking and I've emphasized the product symbol. Here I'm taking the square root of 5x, and that is the same thing as the square root of 5 times the square root of x. So there's my multiplication symbol, and I'm saying that square roots, like the other nth roots, distribute over multiplication. Where students get into trouble is they make the assumption that square roots or any other root distribute over addition, and that is not true. Nth roots do not distribute over addition. So the common error that I see from students is they say the square root of 5 plus x is equal to the square root of 5 plus the square root of x, and that is not true. Square roots do not distribute over addition. Now, usually students don't make the error in this case. Maybe they make the error in a case like this. Maybe they're looking at the square root of cosine squared of x plus sine squared of x, and they think they can distribute that square root over the two expressions, or some other situation. So usually it's not quite as straightforward as 5 plus x and they're taking the square root and distributing. It's usually when they're working with new operations or new expressions or larger expressions than they're used to working with that they end up committing this error. So my reminder to you is that nth roots do not distribute over what operation? Addition. Notice they do distribute over multiplication. They do not distribute over addition. Okay, folks, in the next video, we're going to get to work. We'll actually work some examples. I'll see you in that video.